So first of all, let us see the series combination. So let's suppose we have n resistors connected in series. So suppose we have n resistors connected in series. So this is our first resistor. Okay, this is the second. Let's suppose R1, R2, so on and so forth. We have, let's suppose, n number of resistors. This is R3, etc., etc. Okay. So can you just guess what will be the equivalent resistance of these three resistors connected in series? So this is a battery. Okay, this is a battery which provides the potential difference of V volts. This is simple. It is like you have three wires having lengths L1, L2, L3. Okay, and they might be made up of same material. They might be made up of different materials. Okay, and they are connected in series. So which thing is common for them in series combination? Suppose some current is flowing through this circuit. The current flowing through all of them will be common, right? Current flowing through all of them will be common. So I can say same current flows through R1 also, R2 also, and R3 also. Okay. Then what is the total potential difference? Total potential difference is V. Okay. What will be potential difference across first resistor? It will be I into R according to Ohm's law, right? I into R1. For second one, it is I multiplied by R2, and for third one, it is I multiplied by R3. Okay, so we can say that total potential difference V is equal to potential difference across the first resistor plus potential difference across the second resistor plus potential difference across third resistor, and that is this I multiplied by R1 plus I multiplied by R2 plus I multiplied by R3. This is I can write this as current multiplied by equivalent resistance of series combination. So what is RS? RS is equivalent resistance of the series combination, right? So now I can take I common and I can cancel it out. So what do I get? I will get RS is equal to R1 plus R2 plus R3. Okay. So RS is equal to what? R1 plus R2 plus R3. This is for three resistors. If we have n resistors connected in series combination, then for n resistors connected in series combination, RS will be just equal to what? R1 plus R2 plus so on and so forth up to plus R suffix n. Okay, so I guess this result is very simple, and we have been studying this since 10th standard. Suppose we have n resistors connected in parallel. So let's consider three first. Okay, so this is first resistor R1, this is second resistor R2, this is third resistor R3, and they are connected in parallel, and their common ends are connected to two terminals of a battery. So now what will happen? So potential difference that the battery provides, it is V. Okay. Now what happens is, see, we can think of some electrons. They are coming from here. Okay. They come till this point, and at this point, they have three paths to go. So some will enter this path, some will enter this path. I'm sorry, and some will enter this path. Okay. So current I can say through this circuit is I. See, at this point the current will get divided in three parts. At this point the current gets divided into three parts. Current flowing through R1 is suppose I1, current through R2 is suppose I2, and current through R3 is equal to I3. So now this is parallel combination. Okay, so what will be potential difference across all these resistors? So potential difference across this first resistor is equal to potential difference across the second resistor, and it is equal to potential difference across third resistor, and it is equal to V, right? So I can say in parallel combination, potential difference is common. Potential difference across all these resistors would be same. Okay. So in parallel combination, potential difference is common. So I can say that current through first resistor is suppose I1. Okay, so V can be written as I1 R1. It's equal to I2 R2 according to Ohm's law, and it is equal to I3 R3. And if we combine these three resistors and we say that there would be some equivalent resistance of this parallel combination, then current through that equivalent resistance is equal to what? It is total current, right? It is the total current I multiplied by that equivalent resistance. Okay, so here I can say that yeah, suppose that Rp is the equivalent resistance for this parallel combination. So what will be the potential difference across Rp? Potential difference across Rp is also same because equivalent resistance is connected between the same 2 points where two ends of all three resistors are connected. Okay, so I can say V is equal to therefore I multiplied by Rp. Okay, then after that I can say the total current I gets divided into three parts, I1, I2 and I3, and therefore I is equal to I1 plus I2 plus I3. Okay, and then I can write I equals to V upon this Rp, I1 equals to V divided by R1, I2 equals to V divided by R2, and I3 equals to V upon R3. Okay, so this can be written as V upon Rp is equal to V upon R1 plus V upon R2 plus V divided by R3, right? So then you can cancel out V. So you get 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So this is the equivalent resistance of the parallel combination. This is equivalent resistance of parallel combination. So in case of a parallel combination, what do you have? If you have n resistors, okay, and Rp is their equivalent resistance, then you have reciprocal of that equivalent resistance 1 upon Rp equals to sum of the reciprocals of all the resistors. Okay, so this thing also we have studied earlier, right, in 10th or something. So for n resistors, you can say for n resistors 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus so on and so forth up to plus 1 upon Rn. Okay, so this is the result, right, for n resistors. Now for the case of two resistors, we have to memorize the result because it comes very often. Okay, so we should be directly able to write down the equivalent resistance of parallel combination of two resistors. So for two resistors, let's suppose R1 and R2, we can write 1 upon Rp is equal to 1 upon R1 plus 1 upon R2, and therefore now you can multiply the first one, this first term with R2, second term with R1, and you will get what? 1 upon Rp equals to, in denominator you get R1 R2, and in numerator this is multiplied with R2, this one is multiplied with R1, so you get R2 plus R1, right, or R1 plus R2. Okay, R1 plus R2. So this is 1 upon Rp. We want Rp, resistance in parallel combination, is R1 R2 divided by R1 plus R2. Okay, so for the case of two resistors, we should be able to write down quickly that it is equal to R1 R2 divided by R1 plus R2. So let's consider a resistor like this. Okay, a wire whose resistance is R, capital R, and it is connected to a battery. Okay, it is connected to a battery, right? And this battery provides some voltage V, voltage meaning the potential difference is V. So when we connect this external resistor across this battery, it provides potential difference equal to V. Okay, so there is some mechanism happening inside the battery, some chemical reaction is happening, and due to which it maintains this potential difference, due to which it maintains the potential difference equal to V. Okay, so when we connect some external resistance, what happens? Some current flows through this circuit. Okay, some current flows through this circuit, and then the potential difference at the ends of the battery, at the terminals, two terminals of battery, is equal to V. Okay, now suppose there is no current flowing through the battery. In that case, if you measure the potential difference across the two terminals of battery, that is known as EMF. That is known as what? EMF. So now see, what is the difference between when current is flowing and when current is not flowing. So we have connected this external wire which has some resistance, but the battery is also made up of something. Okay, there are two electrodes and some electrolytic solution is there. Okay, so it is also some material. It will also have some resistance. It is very small, but it will have some resistance. Okay, so the internal resistance of the battery, it is denoted by small r. Small r is the internal resistance of battery. Okay, so now this is inside the battery. Okay, the resistance inside the battery. Now this is our battery. This is our battery, and these are the two ends of the battery which are connected to this external resistor. So then current flowing through the external resistor is I. Okay, so now the potential difference that we get between these 2 points, okay, between these 2 points, see the points of these 2 points is V. V is equal to what? Current flowing through this resistor multiplied by the resistance. Okay, so now same current would be flowing through the internal resistance also. Okay, battery maintains that much current, so same current is flowing through the external resistance as well as the internal resistance. Okay, so same current flows through the resistance small r also. Okay, so you have this battery. Okay, you have the cell. Now there is no current flowing through it, and you measure the potential difference between these 2 points. Okay, between the positive and negative terminal. So you will get the maximum potential difference between these 2 points when there is no current flowing. And now see, once current starts flowing, what will happen? So there is some internal resistance, right? There is some internal resistance. Okay, let me draw internal resistance also. This is R. When there is no current, you measure the potential difference between these 2 points, it will be maximum. Now when current starts flowing, how much would be the potential difference? So it will be the earlier potential difference minus the potential drop here, minus the potential drop, okay, across this resistor, which is equal to that current multiplied by this resistance. So now the potential difference that it provides is equal to what? It's potential difference without the flow of current minus the potential difference across this resistance, the internal resistance. Okay, so the EMF is maximum potential difference that is there between the two terminals of a battery. Got this? Yes, no? Okay, now I want potential difference between these 2 points. So V between potential difference between 2 points will be equal to the EMF. EMF will denote by letter epsilon. Okay, so epsilon is EMF minus I multiplied by R, minus I multiplied by R. Okay, and if you want to find out the current, okay, so let's find out current. So for that, see, the total potential difference is epsilon. Okay, so I can say epsilon is equal to I multiplied by the equivalent resistance of this circuit. What is that equivalent resistance? The external resistance plus the internal resistance, right? It is the external resistance plus the internal resistance. So it is equal to R, capital R plus small r, and therefore you get that I is equal to EMF divided by the total resistance R plus small r. And if you want to find out the potential difference when the current is flowing, so V is equal to what? Potential difference across this resistance or between these 2 points, we can say it's same. Okay, so it is equal to I multiplied by external resistance. So it is equal to this epsilon divided by R plus R multiplied by R. This is the potential difference. This is the potential difference across the resistor, external resistor. Got this? Yes, no? Now, see, we have defined potential difference between the two terminals of a battery is equal to the EMF of battery minus the current flowing through the battery multiplied by its internal resistance. And now you can understand the definition. Okay, so if no current is flowing, this second term will be 0. Then potential difference will be equal to what? EMF. Then potential difference will be equal to EMF. But if current is flowing, what will happen? There will be some drop in the potential difference. How much drop? So specifically, I multiplied by small r will be the drop. Okay. So when is the potential? So when is the potential difference between two terminals of battery maximum? When the current flowing through the battery is 0. Okay. And suppose you are given with 3 cases, that I1, I2, I3 are current flowing through some circuit. Okay, so it is current provided by the battery to some external resistors. So now in which case the potential difference across the terminals of battery would be maximum? So the case in which current is minimum, the potential difference would be maximum, because the potential difference is the EMF minus I into small r. So EMF is constant, small r is constant. What is changing? I is changing, right? I is changing. So if I is minimum, that means there is minimum potential drop. So if drop is minimum, that means the voltage, the potential difference is maximum. Is this point clear? So suppose we connect two cells in series. So this is my first cell. It has some EMF and some some internal resistance. So it is epsilon 1 is the EMF, R1 is the internal resistance of this one. Then I take another cell, it has EMF equals to epsilon 2 and its internal resistance is suppose R2. And I connect them in series combination. What will happen if I connect them in series combination? How much would be the net EMF and net resistance? So for that, we can connect them to some external resistance. Okay, so this is suppose the external resistance for understanding. Right? This is R. Current flowing through this circuit is suppose I. So how can we find out I? So now the total EMF would be equal to it will have some value. Okay, then this resistances R1, R2 and this R, they are connected in series combination. Okay, so there will be some equivalent resistance of the series combination which will be equal to R1 plus R2 plus R. Okay, so it is very simple. See, the potential difference between these 2 points is suppose V1. The potential difference between these 2 points is V2. Okay, the potential difference between these 2 points will be equal to V1 plus V2. Right? This is suppose point A. This is point B. So suppose potential difference. Let's suppose V1 is the potential difference across A1 first cell. I can say V2 is potential difference across second cell, right? So how much is potential difference across the combined cells? Okay, if you consider the series combination of two cells, how much would be potential difference? It will be V1 plus V2. Potential difference between these 2 points plus potential difference between these 2 points is equal to potential difference between A and B. Okay, so I can say potential difference across A and B. So VAB is equal to what? V1 plus V2. And now we know how much would be the potential difference. So VAB is equal to V1 plus V2. What is V1? It is epsilon 1 minus I multiplied by R1. See, this is series combination, so same current flows through all of the resistances. Okay, so epsilon 1 minus IR1. Then we have V2, so plus it is epsilon 2 minus I into R2. So this can be written as epsilon 1 plus epsilon 2 minus I multiplied by R1 plus R2. This is total potential difference, VAB. Okay, and I can write this as total potential difference. I can write this as the total EMF, E equivalent you can say, not E, it is epsilon. Okay, epsilon of series combination minus I multiplied by the equivalent internal resistance of series combination of two cells. Okay, so epsilon S is what? See, potential difference across a cell can be written as what? It's EMF minus I into its resistance. So if you think that this is one complete cell, one battery, what is its EMF? It is suppose epsilon S, S for series combination. Okay, what is its internal resistance? It is RS. Okay, S for series combination, right? So I can write V is equal to epsilon minus IR. Okay, and because epsilon is epsilon S and R is RS, so it is epsilon S minus I into RS. Okay, so this is equal to, on right hand side you have epsilon 1 plus epsilon 2 minus I into R1 plus R2. So if you compare the EMF terms and the potential drop terms, then you get epsilon s is equal to epsilon 1 plus epsilon 2. Rs is equal to R1 plus R2. Okay. So comparing, you get that epsilon s is equal to epsilon 1 plus epsilon 2. Rs is equal to R1 plus R2. So that means if you connect n cells in series combination, what will happen? The total EMF will be equal to sum of EMFs of all the cells. Okay, and the total resistance is the sum of internal resistances of all the cells, right? So for n cells, you can say ES is equal to epsilon s is equal to epsilon 1 plus epsilon 2 plus so on and so forth up to plus epsilon n, and Rs is equal to R1 plus R2 plus so on and so forth up to plus R suffix n, right? So is it clear? So let us see parallel combination of cells. So now we have these two cells connected in parallel combination. Their EMFs are epsilon 1, epsilon 2. Internal resistances are R1 and R2. And we want to find out the equivalent EMF and equivalent resistance. So equivalent resistance is simple, that this is a parallel combination. So it will be the resistance of parallel combination. Okay. Now what about EMF? So for that, we'll start with the current. Okay. So let's suppose I1 and I2 are the current flowing through these two branches, or current flowing out of these two cells, we can say, which have EMF equal to epsilon 1 and epsilon 2. So the two currents combine at this point, the total current is I. Okay. So we can write that I is equal to I1 plus I2. Right. We can say I is equal to I1 plus I2. Then we can write that this epsilon 1, the EMF here, is equal to the potential difference between points A and B, okay, VAB, plus the potential drop in this resistor, okay, the potential drop in this resistor, okay. So I can say it is I1 times R1, right? So from this we can find out the value of I1. What will be I1? I1 will be equal to epsilon 1 minus VAB divided by R1. Okay. Similarly, we can say the second cell is also connected between same 2 points. So here also current is I2. So we can say that epsilon 2 is equal to the potential difference, okay, plus potential drop between these 2 points. Okay, between this resistor. Right. So epsilon 2 is equal to VAB plus I2 R2. Okay, potential drop across second resistor. And then we can find out I2 from here. So what do we get? We get epsilon 2 minus VAB divided by R2. So let's call this one equation number 1. This one is equation number 2. This one is equation number 3. So let's put the equation 2 and 3 in equation 1. Okay, so we can write that I is equal to what? I1 plus I2. So what is I1? Epsilon 1 minus VAB divided by R1, and this is epsilon 2 minus VAB divided by R2. Okay. So after that what we can do is we can group the terms containing EMF on one side and terms containing the potential difference on other side. Okay. So I mean we can group terms containing EMF and terms containing the potential difference. So I can say it is epsilon 1 divided by R1 plus epsilon 2 divided by R2. These are terms containing the EMF. Then I can take potential difference VAB common, because I will have VAB divided by R1, okay, minus of VAB upon R1 minus VAB upon R2. So minus VAB I will take common. So what do I get? I get 1 upon R1 plus 1 upon R2, right? Okay, and what is this? So this is the resistance of parallel combination. Okay, this is the resistance of, actually reciprocal of resistance of parallel combination, right? So what we can say is it is equal to, okay, so this is V divided by R. Okay, so it is epsilon 1 upon R1 plus epsilon 2 divided by R2 minus VAB upon RP, I can say. Okay, so now it is in this form. See, it is in which form? So here we have current. Okay, we wrote current in the first resistor I1 as the EMF here, which is epsilon 1 minus the potential difference between these 2 points, okay, divided by this resistance. Okay, then we wrote current for this one I2 is equal to epsilon 2 minus VAB, okay, minus VAB divided by R2. So similarly we can say the total current is I1 plus I2. It is equal to the total EMF, okay, the total EMF minus potential difference divided by total resistance. Okay, so can we say that? Yes, no? We can write this as, what I am saying is, we can write this as this total EMF is suppose EP divided by total resistance is RP, okay, minus potential difference is same because we are finding out the potential difference between the same 2 points, right? So total EMF will be between these 2 points only. So just like we wrote I1 is equal to EMF, okay, this EMF minus the potential difference, okay, minus potential difference is VAB divided by R1, okay, then, right, so I will keep this term as it is, okay, VAB multiplied by 1 upon R1 plus 1 upon R2, I will keep it as it is. So now I can write the left hand side. So left hand side is also current. So I can write it as EMF minus potential difference divided by the total resistance. And what is total resistance? So I will write it like this. So it is EMF minus the potential difference, sorry, EMF minus potential difference divided by total resistance. So total resistance turns out that it is resistance of the parallel combination. Okay, so then we can separate this. So we can write this term as EP divided by RP minus VAB upon RP. It will be equal to this term minus this term. Okay, so we can write this as EP upon RP. So now we can equate the terms containing EMF and EMF on both sides, terms containing potential difference and potential difference. So what do we get? So comparing the terms containing EMF, okay, comparing terms containing EMF, what do we get? We get that EP divided by epsilon P upon RP is equal to epsilon 1 upon R1 plus epsilon 2 upon R2. And then we can multiply this right hand side by RP. So we get epsilon p is equal to Rp multiplied by epsilon 1 divided by R1 plus epsilon 2 upon R2, right? So we got the equivalent EMF, okay? And then comparing the potential difference, we get the value of resistance, okay? So VAB divided by RP is equal to, so we get VAB upon RP is equal to VAB multiplied by 1 upon R1 plus 1 upon R2, okay? And we can cancel out VAB and VAB. So we get 1 upon Rp is equal to 1 upon R1 plus 1 upon R2. So this is nothing new. We know this, right? Okay, resistance of parallel combination, reciprocal of resistance of parallel combination is sum of reciprocals of all the resistances connected in parallel combination. Okay, so this is, okay, we can write 1 upon Rp is equal to 1 upon R1 plus 1 upon R2. Right, and this is the formula for EMF in parallel combination. Got it? Yes, no? We can say for n equivalent cells, okay, if n cells are equivalent and their EMF is suppose epsilon, having EMF equal to epsilon and internal resistance equal to R. So what will be uh, the net EMF? Okay, so we can find it out using this formula. So what will be net EMF? So epsilon P will be equal to, you can say Rp will be equal to what? If n resistors are connected in parallel, so Rp will be equal to R upon n, right? It is equal to epsilon upon R plus epsilon upon R plus so on and so forth up to plus epsilon upon R. Okay, this will be n times. This is n times, right? So what do you get? You get R upon n multiplied by n times epsilon upon R. This R and R gets cancelled, n and n gets cancelled. So you have epsilon P is equal to epsilon. Okay. So if you connect identical cells in parallel combination, what happens? The net EMF remains same. Okay, EMF doesn't change.